So let's talk about Galilean relativity. So let's just start out with the example of I have a car, or a bus, sort of the way I've drawn it, and I have a kid on the back row throwing a baseball forward. So when we talk about the velocity of an object, or even speed of an object, it's always relative to something. And right now I'm sitting at the desk, but does that mean I am at rest? Well, I'm at rest relative to the desk, but I'm not at rest relative to a bird flying overhead. The Earth is also spinning, and so I'm not at rest relative to the sun. And the sun is moving around the center of the Milky Way, and the Milky Way is moving out, so it's always relative to something. Typically, though, in everyday language, we talk about speeds relative to the ground, or in this case, velocity, since direction matters. So let's just make to the right positive. And let's say that this bus is going 50 miles per hour. The more formal way of stating that is the velocity of the bus with respect to the ground is equal to positive 50 miles per hour. That's a more formalized way of doing it. In this notation here, this first notation is the object, that is the bus, and the second one is the reference. So the velocity of the bus, so I'll put a little b here for the bus, velocity of the bus with respect to the ground. Now this kid here is traveling the same speed as the bus, so this is also equal to the velocity of the kid with respect to the ground. Now he is throwing a ball forward, and since we're using B for bus, why don't we just label this as sphere, S for sphere. And so the velocity of the sphere with respect to the kid, and he's throwing it at 60 miles per hour relative to himself. So from his point of view, he's not moving. The ground around him, the ground is moving into the negative direction, but he himself is moving to the right at 50 miles per hour relative to the ground. So how fast is the ball? What is the velocity of the sphere with respect to the ground? Well, if the bus is going 50 miles per hour relative to the ground and the ball is going 60 miles per hour relative to the bus, well, it's going 110 miles per hour. Positive. So the velocity of the sphere with respect to the ground is equal to the velocity of the sphere with respect to the kid plus the velocity of the kid with respect to the ground. Now, how do I know that this is a valid equation right here? Well, it turns out that as long as those two letters are the same, that the reference point of the first vector and the object of the second vector are the same, then it is valid math. And I did this in one dimension, but it doesn't necessarily have to be. So if the bus is traveling in this direction, so this is the velocity of the bus with respect to the ground, and he throws it at an angle here, so he is throwing the velocity of the sphere with respect to the kid, so this would also be the velocity of the kid with respect to the ground, is in that direction. Well, we can figure out what the velocity, this relationship holds true, whether it's one-dimensional or multi-dimensional. And so what I'm going to do is I'm going to take the velocity of the sphere with respect to the kid, and I'm going to add to it the velocity of the kid with respect to the ground. So that would be the vector of the velocity of the sphere with respect to the ground. This is the velocity of the sphere with respect to the kid, velocity of the kid with respect to the ground. Now notice that we can manipulate things around a little bit. If I subtract this from both sides, then our equation ends up being velocity of the sphere with respect to the ground minus the velocity of the kid with respect to the ground is equal to the velocity of the sphere with respect to the kid. Now I don't have those letters the same, but if I just flip that, I can, but let's think about what that means. That, again, if I have the kid here with respect to the ground, the kid is going this way with respect to the ground, but if we think of the kid as at rest, that means the ground is traveling in the other direction. So if I flip the reference and the object, I'm changing the direction of the vector. In other words, the sign changes. And so this becomes the velocity of the sphere with respect to the ground plus the velocity of the ground with respect to the kid is equal to the velocity of the sphere with respect to the kid. Let's just make sure that math works out. We had velocity of, so this was 110 miles per hour. That was positive. Velocity of the ground with respect to the kid, that's going in that direction. That's minus 50 miles per hour. And that would be 60 miles per hour, which is the velocity of the sphere with respect to the kid right there. And that is the essence of Galilean relativity.